All right, so in the last video, I was talking about the calculus of trigonometry, but I was talking more specifically about the basic six trig functions and how to take their derivative and how to integrate them. So, we were talking about sine, cosine, tangent, cotangent, secant, cosecant. But so I skipped over a couple of the interesting integrals, like, for instance, the integral of tan x dx. Now, if you recall, and I wrote it over here on the left side, the only time tangent ever appeared in an integral was right here, where it was combined with secant x, because secant times tangent is the derivative of just regular secant. And so it was a nice, easy to do integral, just doing the antiderivative, working backwards, saying, hey, I know what the derivative is. I want to know what the original function was. So the question is, in this situation with tangent x, I need to think about it and say, okay, I know tangent's the derivative, but what's the original function? And so probably the best way to handle this problem will be to, remember back to your trigonometric days and to write tangent x as a ratio of sine and cosine. Now that I've got that taken care of, we can do an actual u substitution. So the u that I'm going to use, and I'll switch colors, is I'm going to do u equals cosine x. I'm going to take that denominator there, and I'm going to switch it out for a u substitution. That means that my derivative du of cosine x, hopefully you guys remember again, is my sign changes, so this is going to be a negative sine of x dx. So when I do this u substitution, it started off positive, but it's going to end up being negative because of that negative sine x right there. So I'm going to go ahead and work on that u substitution. So I'm going to integrate essentially 1 over u, and I'll call it a negative du. So what I'm going to do just briefly is rewrite this as 1 over u as u to the negative 1. And I'm going to take this negative sign and I'm going to move it out using that constant multiple rule. So there's the negative on the outside. Hopefully you do remember that if I want to integrate 1 over u, or u to the negative 1, that does involve a natural logarithm. So it's going to be the negative natural log of the absolute value of u plus c, plus our constant of integration. Now that I've got that taken care of, I'm going to go ahead and remember to plug back in my original variable. So in this case, the cosine of x. So I'm going to look at a final answer of the negative natural logarithm of the absolute value of cosine x plus c. Now, it is important in this situation to remember to include those absolute values. And the reason this is important here is because cosine is not always positive. It has some parts that are positive and some parts that are negative. So again, remember to include that little tidbit of information because that is vital in making sure that this function has all of the values it's supposed to have. Following a similar train of logic, we can do the same idea with cotangent as my integrand, as what I want to find the integral of. So again, the first step here is to, again, write it as a ratio of sine and cosine. In this case, cotangent is cosine x over sine x dx. And we're going to do a very similar u substitution. We're going to switch out that denominator, which in this case is sine of x. And that derivative is positive cosine x, so this sign won't have to change. So when I do that, we will get the integral of 1 over u du. And again, that's going to turn into a natural logarithm, so natural log of the absolute value of u plus c. And the last thing I need to do is remember to switch back to my original variable. So take that u and switch it back out for sine of x. So we'll have the natural log of the absolute value of sine x plus c as the final answer for the integral of cotangent x. Now, these are, again, two special integrals, but there are a couple of others, and that's kind of the important question here is, if I didn't take an integral of tangent or cotangent before, let's follow the same logic. What about what happens if I do the integral of secant x? Because, again, I have some integrals with secant in them, like secant tangent and secant squared, but what if there's no secant squared or no extra tangent? What if it's just a secant by itself? Well, this one is a little bit different. It's not going to follow the same rules as doing tangent and cotangent, but there is a sort of manipulation that does need to happen in this case, and I'll show you what that is. It will again involve a u substitution in the end, but there is a manipulation that has to happen before then. What I'm going to do is I'm going to multiply the top and bottom by secant plus tangent. Now that's going to be important here, and you'll see why in just a moment. So again, I'm multiplying top and bottom by secant plus tangent. So what that's going to happen is I'm going to end up having secant squared times secant tangent in the numerator. Let me write that down. Secant squared plus secant tangent in my numerator divided by just secant x plus tangent x. Now, here's where the u substitution comes in. It's important to note that, again, I want to make a u substitution for whatever's in that denominator. Okay? So, if I take this denominator, secant x plus tangent x, and I find its derivative, well, come back up here and kind of look for a second, is if I have secant x, its derivative is that secant tangent. Well, that's kind of important here for a second. So let me write that down. Secant x tan x. And the derivative of tangent x, come up here and look at it, tangent x, the derivative of it is secant squared. Okay. Dx. Well, if you notice, that's exactly what my numerator is, except for maybe the order. So I've got my secant x tangent x, and I've got my secant squared in that numerator. So essentially, this really is, if I make my u substitution, just the integral of 1 over u du. No sign changes are necessary for this one. So again, this 1 over u is going to involve that natural logarithm. So I'll write it as ln of u plus c. And again, I need to go back and remember, hey, what was that u that I switched it out for? What was that original variable? Well, in this case, it was secant x plus tangent x. So my final answer is going to be the natural logarithm of the absolute value of secant x plus tangent x. All right, now that one handles that. And again, the last thing that I need to look for is, I've kind of done tangent, cotangent, secant. I'm just missing cosecant at this point. So let me kind of section this off a little bit better. All right, so we're going to integrate cosecant x dx. And again, I'm going to follow the same idea that I did with secant. I'm going to multiply the top and bottom by, in this case, I want to do cosecant and cotangent. And I'll still do plus. And you'll, again, see why in just a moment. So when I multiply this out, when I'm, kind of do the cosecant on top, so we'll integrate cosecant squared of x plus cosecant x times cotangent x over cosecant x plus cotangent x dx. Now, again, do a nice u substitution. We're going to do the denominator again. So cosecant x plus cotangent x. And what we need to remember here is when we take the derivative of these co-functions, the cosecant and the cotangent, the sign is actually going to change. But nice thing about this is every sign is going to change. So we're going to have the derivative of cosecant, which is going to be negative cosecant x cotangent x. And then we're going to also have the derivative of cotangent, which is negative cosecant squared x dx. Now, again, all of the signs changed. So when I do this u substitution, we're going to integrate 1 over u essentially times negative du. All of those signs change. So I'll do this in red. This was a negative cosecant squared and a negative cosecant down here in my du part of the u substitution. So by making that a negative, we kind of handle that situation. So I can still, again, do like what I did before and take out that negative using the constant multiple rule. And so we can essentially just integrate that 1 over u, which is the natural log of the absolute value of u. I don't want to forget my negative sign, plus c, which, again, remember to switch back to your original variable. That's the important part. We'll get the negative natural log of cosecant x plus cotangent x in absolute values plus c. Now, I do want to point out this still kind of follows my same rule that I had before, where if I find my final answer has a co in it, a cosine or a cosecant or a cotangent, then it's going to have that sign change from positive to negative. Notice the ones, sine, secant, and tangent, don't have an opposite sign. You know, I didn't go from positive to negative or from negative to positive, but the ones with co in them did. Now, hopefully this helps kind of clear up any questions about the remaining trigonometric integrals. Now, we'll come back and talk more about trigonometric integrals when we do inverses and some of the other